let's say we wanted to look at the following series. Sum from n equals 1 to infinity of 1/2 to the n, which you might have seen before. It's a pretty typical example, but it's worth looking at anyway. So if I start writing this out, I'm going to get 1/2 plus 1/4 plus 1/8, and so on and so on and so on. And while we could look at the sequence of partial sums, sorry, you can't see me very well. Yeah, but I don't like to not see you. And also there was something else I wanted to do. Oh, yeah. There we go. Let me do one other thing here. Cool. I'm sorry. So we've definitely looked at this one before. We talked about the sequence of partial sums, which is not what we're going to do, but I will remind you, like, the first partial sum is 1/2. The second partial sum is 1/2 plus 1/4, which is 3/4, and so on. And so one way to look at if a series converges is to see if the sequence of partial sums converges. But that's usually kind of a long and tedious way of doing it, and it's not always particularly easy to do or what we're going to do. For geometric series, we have kind of a specific thing that we look at. So let's look at a very general idea. We'll come back to this example. So let's say we have the series, the sum from, I like to write it this way, n equals 0 to infinity of a times r to the n. When we start writing out terms, we're going to get a plus a times r plus a times r squared, plus a times r cubed, and so on and so on and so on. And what I want to point out is what makes this a geometric series is that each subsequent term is the previous term multiplied by the same ratio, which is why we call it r. So to get from here to here, we multiply by r. From here to here, we multiply by r. And so on and so on and so on. That's the hallmark of a geometric series. So I want to figure out how to deal with this. I really do want to actually look at the nth partial sum. So let's look at S sub, I'm going to use slightly different notation here, S sub n minus 1. So that's going to be the sum from n equals 0 to capital N minus 1 of this same thing. So let's see. Instead of stopping at never, I'm going to stop at n minus 1. So I'm going to get a plus a times r plus a times r squared plus all the way to a times r to the capital N minus 1. And so far you might be thinking, well, I don't really know what a pattern for that is. Here's how we're going to do it. We're going to multiply that by r. So r times this, I'm going to just multiply each term by r. So I'm going to get a times r plus a times r squared plus all the way to a times r to the n minus 1 plus a times r to the n. Look good so far? Okay, now all I'm going to do is subtract them. So I'm going to do this one minus this one. So S sub n minus 1 minus r times S sub n minus 1 is equal to, well, looks like a bunch of stuff is going to cancel. I'm going to get a minus a times r to the n. Welcome. Let me see your symptom survey when you have a moment.
I don't have it.
I need to see it.
Okay.
Sure thing. And now we can use algebra to actually solve for this n minus 1 partial sum. So we're going to get Sm minus 1 times 1 minus r equal to a times 1 minus r to the n. And then, of course, I've run out of room at the key point here. On paper. The paper doesn't want to do the thing paper does. And then we're going to see that the n minus 1 partial sum is equal to a times 1 minus r to the n divided by 1 minus r. Or if you wanted to go to the next term, you could say the nth partial sum is a times 1 minus r to the n plus 1 over 1 minus r. Thank you so much. There's a number of ways of doing this. Like sometimes people start at 0 instead of 1 and get something a little bit different, or start at 1 instead of 0 and get something different. But this is the general idea, is that we can write the nth partial sum as this value. So looking back at our particular expression, if I look at the sum from n equals 1 to infinity of 1/2 to the n, it's going to equal, well, of course, I did it a little bit differently. Well, we're going to get some, well, actually, that's not quite what I want to do. Sorry. If I look at the, say, 10th term, it's going to be, well, my first term, 1/2 times 1 minus 1/2 to the 10th over 1 minus 1/2. Oops, sorry, you guys want to see that. Maybe it's a +1 here. Sorry. Wow, that's really hard to read, isn't it? I can barely see that. Let me write that again. But here's the idea, is that we can see that as this index gets larger, this part here, this power here, gets larger. Now here's the important part. If this ratio that we're multiplying each term by is a number that's between 1 and -1, then this thing raised to a higher and higher and higher power is going to get smaller and smaller and smaller. Exactly. So we can say that if you can either write it as the absolute value of r is less than 1, or r is between -1 and 1, then the limit as n goes to infinity of r to the n is going to be 0, which is going to mean that this sequence of partial sums, right, this partial sum, its limit as n goes to infinity of Sn, which will be the limit as n goes to infinity of a times 1 minus r to the n plus 1 for 1 minus r. Well, this part is going to go to 0. And so we're going to get a over 1 minus r. Welcome. May I see your symptom survey when you have a moment? Excuse me. Can I see your symptom survey when you have a sec? The symptom survey, you know, the little green one that we fill out. Sure. So what I'll say is, I wouldn't recommend memorizing this particular formula. It's not exactly what you want because it's very particular. So let's be a little more general. So here's what I would tell you. This formula, that one I just wrote down, is good for this particular series. If you're starting at n equals 0 and going to infinity, that's going to equal a over 1 minus r. If the absolute value of r is less than 1. And it's going to diverge otherwise. But things aren't always written in this nice way. For example, well, our previous example, actually, what about this sum here? Sum from n equals 1 to infinity of 1/2 to the n. That's not written in this exact format. We could make it so it was, but we don't want to have to do that. So here's what I'm going to point out. a better way of figuring out what these things converge to is by using this more general formula, which is the following. These geometric series converge to the first term, whatever that is, divided by 1 minus the ratio, assuming they converge. So in this case, that's going to be 1/2 divided by 1 minus 1/2, which is just 1, which is what this definitely does converge to, right? Our terms are 1/2 and then 3/4, then 7/8, then 15/16, right? Each time getting closer and closer and closer to 1. But this works kind of for any weirdly written thing. For example, if I want to find what this series converges to, I don't want to have to think about what my A thing is and what my starting 0 thing is. I can say, well, what's my ratio? What am I multiplying by each time to get to the next term? It's not immediately obvious the way I've written. There's a couple ways to discern what my ratio is. One way is to start writing out terms. So if I start writing out terms, okay, my first term is going to be, well, when n equals 2, I'm going to get 5/9. And then my next term, when n equals 3, I'm going to get negative 5/27. And then my next term is going to be positive 5/3⁴. And then my next term is going to be 5/3⁵. So it looks like every time I'm multiplying by what to get to the next term? Well, the numerator is staying the same. The denominator is multiplying by a factor of 3. So it looks like I'm multiplying by 1/3. But what else do I need? What's that? So I see what you're saying, right? We need to kind of account for this -1 to the n here. We really should be multiplying by -1/3 each time. To get from here to here, multiply by -1/3, yeah, that works. From here to here, multiply by -1/3, that works. So one way to see what your R is to literally just write out terms. And if every term is the previous term multiplied by the same thing, that's your R. You have a geometric series. Alternatively, if you can rewrite your expression so you have one thing raised to the nth power, that's also a way of finding your R. So you could rewrite this as the sum from n equals 2 to infinity of 5 times -1/3 to the nth power. And that would be another way of seeing, oh, there's my R. Because each subsequent term, you're just going to have the next highest power of n, which means you're going to be multiplying by the next highest power of your ratio R. Okay, what does this converge? Well, first of all, does this converge? Is my ratio a value where this should converge? Yes. Yeah, right, because our R is definitely between -1 and 1. So this does converge. Oh, I forgot to write the rest of the statement here. What does this converge to? Well, it converges to my first term. Let's say my first term is 5/9 divided by 1 minus my ratio. That's it. There are other ways of seeing this. And actually, I feel like I'm always at the end of the paper at the wrong moment. So let me write down here. Right, this is equal to 5 times -1/3 to the nth, and that is 5/9 minus -1/3, which we should simplify. 5/9 4/3, which is 5/9 times 3/4, which is 5/12. Okay, but some people are kind of like, James, if your formula feels a little unsupported, you might be right. So here's what you can do if you don't like this, just to kind of point out another way to see things. This sequence, sorry, this summation. I would really rather it look kind of like the usual thing, where you start with some, you basically you're starting n equals 0. So we could rewrite this. We could say, well, this is going to be the sum from n equals 0 to infinity of some a times r to the n. I know that my r has to be negative 1/3. What do I need a to be to make this work? Well, when n equals 0, I'm going to get 1. So a, I guess, has to be 5/9. There's my a. There's my r to the n. And look, it's exactly what we said it should be. Now, if you write it this way, the answer is it's a over 1 minus r, which is 5/9 over 1 minus 1/3. So here's the point. Some people get really hung up about this, about writing it this way, where you start at the 0th term and you go on and on and on. I don't think you need to do that. I think the nicer way of seeing what a geometric sum or series converges to, if it converges, is just by finding the first term, dividing by 1 minus the ratio. It always works. There's no like, sometimes it works, sometimes it doesn't. No, this formula always works every single time, as long as it converges. So, let's look at a couple more examples. Let's say we wanted to look at the sum from n equals 1 to infinity of 6 times positive 2/3, that's a 3, believe it or not, to the nth power. Converge or diverge? Converge, definitely. Converge. I suppose I should really ask instead of converge or diverge, because what's my ratio? Definitely. All right, and then we can say it converges to first term. Let's see, my first term is going to be 6. Yeah, you're right. No, definitely it is 4. I'm going to write it out the long way, right? I'm just going to plug in n equals 1, or whatever my starting index is. First term over 1 minus 2/3. And then we can simplify that. You're right, that's totally 4 on top, totally 1/3 on the bottom. So we're going to get 12. That's what this series converges to. Look at 2 or 3 more. But the sum from n equals 2 to infinity of 8 times negative 5/4 to the n minus 1 power. Let's write it a couple terms. Well, no, I don't want to write a couple terms. What's my ratio? Yeah, it is. So if it's raised to the n power or the n plus 1 or the n minus 1 or the n plus 7, as long as it's just n plus or minus a number, each next term is still going to get multiplied by negative 5/4. You could write out terms if you wanted to. This would be, the first term would be 8 times negative 5/4. I don't even really want to figure out what that is. And then the next term would be 8 times negative 5/4. By plugging n equals 3, it's going to be squared. I think, right. But I think writing it out this way just emphasizes the fact that each next term, you're just taking the previous term and multiplying by negative 5/4. And you're totally correct. R equals 5/4 is less than 1, or you could say that the absolute value of R is definitely bigger than 1, and that means that our series diverges. It doesn't diverge in any particular. So you couldn't say, not that it's super important, but like how, oh, sorry, there's people writing things in the chat and I'm totally like not seeing the chat. Sorry, I'm always looking over here and the screen's over there. Let's see, someone wrote, what would it look like if this formula doesn't work? We just have to know it converges. Okay, and then they wrote, it makes sense. Okay, so good. I answered the question without seeing it. Sorry, I'll try to pay a little bit more attention. If you have a question in Zoom and you're not hearing me pay attention to it, you are really welcome to unmute yourself and say words. It might scare me a little bit, but It'll be all right. It's okay if you start. Oh yeah, this series, you couldn't say diverge to infinity or to negative infinity because it actually is bouncing back and forth between larger positive values and larger negative values. Because you're going to add something big and positive, and then something bigger and negative, and then something bigger and positive. You're going to keep getting a big negative number, then a bigger positive number, and so on and so on and so on. Usually we don't care, especially for sums or series, in what way they diverge. We just care that they diverge. Okay, let's look at this fun geometric series. The sum from n equals 1 to infinity of 3 to the 2n plus 1 over 4. Oh, thank you. Over 4 to the n. Welcome. This is Co-21C, and may I see your symptom survey? You can take a seat and show it to me. You're good. So what's the ratio here? It might be good to write some terms out. So let's see what happens. When I plug in n equals 1, I get 3 to the 3rd over 4. When I plug in n equals 2, I'm going to get 3 to the 5th over 4 squared. When I plug in n equals 3, I'm going to get 3 to the 7th over 4 cubed. So it looks like each time I'm multiplying by, well, on the top I'm multiplying by 3 squared. On the bottom I'm multiplying by 4. And that's what's working from here to here and from here to here. So it looks like my ratio is what? Yeah. What does that mean? Right, the series diverges. Now, another way to see this, if you don't want to, because writing out terms is a little tedious. I'm not gonna lie. This is not what I would probably actually do if I was doing this problem. I would probably say, well, I can see that what I really have here is 3 times 3 to the 2n over 4 to the n. And then I can rewrite that as 3 times 3 squared to the n over 4 to the n. And then I can rewrite that as 3 times 9 over 4 to the nth power. And then it's also a way to see that, oh yeah, my ratio is 9/4. Either way, this series diverges. Exactly, yes. So just to clarify, someone asks, finding R will help determine whether it converges or diverges. Yes, for a geometric series. And if it converges, we can use it to find the formula for what it converges to. Also, yes. Now, I will also mention along with that, aside from like 1 or 2 other special kinds of series, this is kind of the only series we usually are able to figure out what it actually converges to. Most sums or series that we look at after geometric, we are not going to actually be able to find what they converge to. The only kind of exception to that are telescoping sums, like we saw last class, and you guys have probably seen in your own 21C classes, where like all the middle terms cancel except for the first and the last one, something like that. Also, we can figure out what it converges to. Yeah. Let's look at one more example. The sum from n equals 1 to infinity of, let's do this one. Sorry, I had something in there. Oh yeah, let's do 5 to the n plus 1 over 2 to the 3n minus 1. It's kind of like a pain in the butt. It's not so terrible. So just like the previous problem, I can't readily see. I mean, you could probably with some practice tell me what the ratio is without too much mental energy, but I like to write it out so I have essentially some quantity raised to the nth power. So I'm going to rewrite this as 5 to the n times 5 to the 1 over 2 to the 3n times 2 to the negative 1. And then I'm going to rewrite that as the sum of, so 5 to the n over 2 to the 3n, that's going to become what to the nth power? I think it's a 5 over 2 to the third. Yeah, 8. Yeah, you're right. 8 is exactly what I was looking for. I was gonna say 2 to the third, but yeah, it's 5 over 8 to the end. And then this 5 over 2 to the negative first is just 5 times 2. Just 10. So this definitely converges because our R is less than 1. I should say the absolute value of R is less than 1. And it converges to my first term over 1 minus R, which in this case is 10 times 5/8 over 1 minus 5/8. I'm literally just plugging in the first value that I start with to get the first term. In this case, I plugged in n equals 1. I got 5/8 times 10. And then I should simplify that. That's going to be 10 times 5/8 divided by 3/8, which is 10 times 5/8 times 8/3, which is 50/3. Cool. One other, you look like you got a question. No, I'm just imagining things. Okay. There is one other kind of geometric, well, there's actually a couple other applications to geometric series. Here's one of them. So someone might ask you to say, write the following repeating decimal. Let's pick something interesting. 0.373737 forever and ever and ever. Write that as a fraction. Or as a ratio of 2 integers is probably the words they're actually using, but fraction. Now, there's a 21C way of doing this. There's also a really slick way I saw like on Instagram the other day. I'm not gonna lie, someone was doing math tricks and I was like, this is super cool. So I'm gonna show you both ways because I just think the other way is super cool. But let's do it the regular math way first. So I'm gonna write this repeating decimal as a geometric series. These are just fractions. I've got, so what I'm really thinking of this as is 0.37 plus 0.0037 plus 0.000037 forever and ever and ever. Or if you prefer, and we do prefer, fractions. 37 hundredths over 37 10,000ths over plus 37 millionths, or let's just be smart about this, 100 squared, 100 cubed, and so on and so on. And I could definitely, actually, I don't even need to write this as a geometric sum. I can see it already is. Each time the ratio we're multiplying by is 1 over 100. So we could totally see that this is going to equal the first term over 1 minus the ratio, which is going to be 37 over 100 over 99 over 100. Those hundreds are going to cancel, and we're going to get 37 over 99. You could also, and it's probably worth mentioning, it's good to be able to write this as the summation. So if I was writing this as a summation, to be the sum from n equals 1 to infinity of 37 times 1 over 100 to the nth power. That's how I would write that. But there is also a neat trick that is, it's not just a one trick pony. It actually comes up in various places. So I think it's not a waste of your time to see it. I try not to waste too much of your time showing you things I just think are neat, but also worthwhile. So here's another way you could do this. Take this number, which we're going to find. We're going to call it x. And let's multiply it by 100. So 100 times x, well, I'm just going to move the decimal over 2 places. So instead of having 0.37373737, I'm going to have 37.373737 forever and ever and ever. And now we can subtract them. 100x minus x is 99x. So this is looking promising. And 37 point all the decimals minus all the decimals, those all subtract and you just get 37. So that the number you're looking for is indeed 37 over 99. Kind of a cool trick. It's actually a useful trick because it shows you a fact that many people don't believe is true. Here's the fact that I want you all to know is true, even though it's, okay, this is not that important for this class, but it is an important thing. This number, 9 forever and ever and ever and ever. And I want to be extra clear about this. It's not like they're close to each other. It's not like one's approximately the other one. They are literally the same number. Just like these are the same number. It's just a different way of expressing the same thing. I know this seems kind of weird, that 0.99999999999 forever is equal to 1, but you could either do this trick here and you'll get it equal to 1, or you could actually write out the geometric sum. In fact, I would encourage you all to check that 9/10 plus 9/100 plus 9,000 plus so on and so on and so on. You can, using the geometric sum formula, show that this is in fact equal to 1. It'd be a good exercise for you all to do. Pretty neat. But the real kind of thing to know here, and again, I'm getting slightly off track, I'll be done in just a second, is if you can't find a number between two numbers, those numbers are the same. There's no number between 0.999999999 forever and 1. You cannot find it. It does not exist. There is no such thing because they're the same. Okay, enough of my soapbox there. Oh, question, yeah.
For that 100, is it always 100 or does it just depend on?
No, so actually that's a fair, you ask a good question and that merits, I think, another example. So, and I feel, and also my example was, I also slightly cherry picked, meaning I could have made it a little more challenging. So let's say we want to, yeah, let's say we have the number 2.365. How many decimals do I want to go here? Let's do that. So basically, the number of numbers that are repeating, that's going to be the number of the power of 10 you need. So I don't know exactly how I'm going to write my series yet, but I know for a fact that my ratio is going to be 1/10 cubed. Now, I know I'm jumping ahead of myself here, but that's what I'm going to end up with. Now, some of this is garbage. Like, I really am not loving the fact that I have a 2.3 here. It's not helping me because it's not part of my repeating decimal. So actually, I'm going to rewrite this as 2.3 plus 0.0654654654654, etc. We can. I was going to try not to use the trick again. I know the trick is cool. I'm not going to lie. I think the trick is cool. But see, actually multiplying by 10. Oh, do you mean like the whole thing?
Yeah. And then you multiply the next one by 1,000 or no, 10,000 and then subtract it. I think what we would want to do if we were going to use that trick is to separate like this and then just to kind of ignore this part and multiply this part by 1,000. I think that's the way I would handle it if I was trying to do the trick. So the trick way, we would have, okay, ignore the 2.3 for a moment. And we're looking at 1,000 times our number, let's call it X. 1,000 times X is going to be just move the decimal over 3 places. So it's going to come after the 5. 654, 654, 654, forever. And then our X is just
0.0654. It is good to line the decimals up to make sure it's easy to see what's happening here. And then we're going to subtract. And oh yeah, we're going to get 999x equal to 65.4. I see why you might have wanted to multiply by 10. It's still going to be fine. So then x is going to be a terrible decimal divided by a number. And yes, I would take your advice now and multiply the top and bottom by 10. Because I really don't want decimals and fractions. That's just terrible. So we should write this as 654 divided by 9,999. It's 9,990. And then finally, I would write my answer as 2.3 plus 654 over 9,990. And then I'd probably actually do something. And I would probably not actually do this because I'm lazy. Oh no, I would, because the question was to actually write it as a fraction, right? So, okay, we probably have to like get a common denominator. So we're going to take this, multiply it by 999 times 23 over 9,990 plus this. And that's terrible, but fine. So we're going to get 23 times 1,000 minus 23 plus 654. Do you guys see the oh.
Boom, one step.
Oh, one step. Okay.
Multiply this one by 10,000, multiply this by 10.
Oh, that's
Subtract
cool.
it.
I like it. Okay. She's got that. You know what? I will admit, when I see good math, I see good math. That's awesome. Yeah. So she's definitely got a better handle on that. I think if you're doing it this trick way, you can definitely, yeah, that's good. I'm like, I like it so much. So wait, let me see one thing. I'm curious. Oh, that's interesting. Yeah.
You just want to line it up.
No, but I hadn't thought about the fact that so I was seeing incorrectly that this was problematic. This isn't problematic. It totally doesn't even matter. So although this is not wrong, it's not elegant. Let's do it a different way. So exactly what she said. I'm sorry, what's your name?
Mia.
Mia. Exactly what Mia said. Let's call it y, since we already used x to our great failure. So here's y equal to 2.3654, etc. So we want, yeah, do you need to do 10,000 or can you just do 1,000? And I'm wondering if you could just do 1,000 though. It's probably better to just do 10,000. So 10,000 y, how many decimal places do I move it over? 4, so I'm going to get 23654.654. Yeah, and then 10y, multiply it, just move it over 1, so you get 2, 3 point, yeah, clever, I like it. Subtract 9,990y equals, this is where I was getting jammed up a little bit, but it works out just fine. 236, and then 5 minus 2 is 3, 4 minus 3 is 1. The rest cancels. Slick. I'm a fan. No need to get a common denominator or any of that garbage. Now, I will mention, this probably won't be the way your teacher would actually talk about it. If I was seeing this problem taught in 21C plus, the way they would probably encourage you to do it is starting with this and then writing out the flaw. So not that you can't do it this way, because I think that's great. And I would encourage you, I think it's really cool. But just so you know what you might see from someone else is, they might say, you should really do it like this. Not the way I did it before, which admittedly was less excellent than it could have been. But to say, rewrite this part as the sum from n equals 1 to infinity of, then you're going to have to rewrite this as like 654 over something times 1 over 1,000 to the n. And I think we need a 654 over, if we multiply by 1 over 1,000, we get 0.654, but I want 0.0654. So I want a 10 there. So that might be how someone would encourage you to do this problem without using this trick. You want to write it as a geometric series, but we've got this kind of terrible thing where our terms are, sorry. Right, this is 654, not over 1,000, but over 10,000. And then the next term is 654 over 10,000 times another 1,000. And then the next term is 654 over 10,000 times another 1,000. And so on and so on and so on. It's not as nice, definitely. But just be prepared that someone might expect you to see it this way. Again, I should also point out, this is not the majority of what we do in this class, right? It's a cool kind of little thing, but you'll probably see like 4 problems on it at the most and then be done with it. It could come up on the test. It probably won't. Probably is maybe a little strong there. I would bet it probably, no, probably is the word I'm going to use. All right, so geometric series. They converge if your ratio is less than 1. You can find what they converge to. It's the first term over 1 minus the ratio. They diverge if the ratio is bigger than 1. I should say bigger than or equal to 1 or less than or equal to -1. That's it. So what about something like this? The sum from n equals 1 to infinity of 1 over n squared. If I start writing out terms, get 1 plus 1/4 plus 1/9 plus 1/16. What I want you all to really be aware of here is that it's not geometric. We are definitely not multiplying by the same thing each time to get to the next term. 1 times 1/4 is 1/4. 1/4 times 4/9 is 1/9. Those are not the same. This is definitely not geometric. And it doesn't have the hallmark of being geometric. We don't have some ratio raised to the nth power. So I should also point out, and this is something I should have probably been mentioning from the get-go, something you should always be in the back of your mind. The nth term test, or also known as the test for divergence, doesn't tell us anything here because the limit as n goes to infinity of the sequence is 0. And when the limit of the sequence is 0, we don't know anything. Our series could do anything. It could converge, it could diverge. We don't know. So we have to do something else. Well, let's take a look. So suppose we wanted to estimate let's say we want to estimate the 100th partial sum. So 1 plus 1 over 4 plus 1 over 9 plus all the way out to 1 over 100 squared. We would love to get an estimate of that. We're not actually going to get an estimate of that, but we'll see what I mean. So let's draw a picture. And I'm going to draw the graph of, oh, not so close there, y equal to 1 over x squared. And I'm going to draw the areas that are going to be helpful. So that first rectangle, this area, and I know I've drawn it very not to scale. My x and my y axes are not to scale. But this first rectangle has an area of 1. I plugged in 1 to my function. 1 over 1 squared is 1. Base is 1, height's 1, area is 1. And this next rectangle has an area of A2. Its base is 1. What's its height? What's the height of that rectangle there? That second rectangle I've drawn. Right, because I'm plugging in 2 to my function, I'm getting 1/4. So that, right, that definitely is the second value of my sequence. And my third rectangle would have an area of A3. All the way out to, I'm actually going to go to my nth rectangle here. This rectangle would have an area of A sub n. Good. Okay. Let's look at a similar but slightly different picture. I'm going to draw the same function. I mean, the same, right? As the same as I can. But now I'm going to draw different rectangles. I'm going to draw the under rectangles instead of the over ones. So I'm going to draw this rectangle here, which has an area of A, because the height's 1/4 and the base is 1. And this rectangle, which has an area of A3, all the way to this rectangle, which has an area of A sub n. Okay, so here's what I want to say. The area of my sequence, sorry, the area of my sequence, the summation S sub n equal to A sub 1 plus A sub 2 plus all the way to A sub n, the nth partial sum. I can say that's between a couple things. I can say that this is definitely bigger than the area under the curve here. So these rectangles, definitely more than this area in red. So definitely bigger than the integral from 1 to n plus 1 of that function. The area is definitely, this summation here is definitely smaller than this area if I add on the first term. So it's going to be less than A sub 1 plus the area under the curve here, which is the integral from 1 to n of 1 over x squared dx. Welcome. So what we're going to say here is that this sum, this nth partial sum, is between these two integrals. And we can figure out what these integrals do because we learned in 21B how to deal with improper integrals. So if I actually want to look at S100 specifically, I can say the integral from 1 to 101 of 1 over x squared dx is less than the sum from n equals 1 to 100 of 1 over n squared is less than the first term plus the integral from 1 to 100 of 1 over x squared. And actually figuring out what that is, come on. We can see that, well, I know how to integrate that. That's going to be the integral of 1 over x squared is negative 1 over x from 1 to 101 is less than this thing. So that's a 1, not a 9. And this is, again, a negative 1 over x. That's a negative 1 over x from 1 to 100. So what do we get here? Well, let's see, if I plug in 100, you get negative 1 over 101 minus negative 1 over 1 less than the summation. You guys can still see the thing, right? Yeah. Less than 1 plus negative 1 over 100 minus (-1/1). So let's see, what do we get here? We have that's 1 minus 1/101, or 100/101 is less than this thing here. And that's less than this here, which is going to be 1 plus 1, so 2 minus 1/100, which is 199/100. So what is this telling us? Well, it's telling us that this summation is bounded. It's between two things. It's definitely got a lower bound, it's definitely got an upper bound. And we know that partial sums are increasing as long as the terms are positive. So this thing, if I keep adding on more terms, is going to get bigger and bigger and bigger. And it's definitely going to be bounded below and bounded above, which means it's going to converge since it's bounded above. So the real idea here is that the series and the related improper integral have the same behavior. Meaning, if one of them converges, the other one converges. If one of them diverges, the other one diverges. So if the integral for the function of the series is convergent, the series is convergent. If the integral for the function of the series is divergent, the series is divergent. This is called the integral test. There's a couple extra restrictions that I should mention, but that's the very basic gist of it. Is that, write it down here. So the integral test says the following. For a positive, continuous, decreasing function, where x is greater than n, if the sequence is the same as the function. Meaning the function can be this nice continuous thing. The sequence is just what you get when you plug in 1, 2, 3, 4, 5, 6, etc. Then what we said, meaning if the integral from n to infinity of the function converges, then so does the series. And if the integral from n to infinity diverges, then so does the series. That's it. And it's one of the tests that after you learn all the other tests, you kind of tend to forget about, but it's actually a really powerful test because as long as you can integrate the thing, you can tell if the series is convergent or divergent. Now, there are a lot of functions we can't integrate very well, but there are a lot that we can. So if you see something that you're able to find the antiderivative of, the integral test is always an option. Let's look at some examples. And again, just to back up a little bit, the reason for this, I hope, is fairly not hard to see, right? We're just saying essentially that if the integral diverges, well, then the series is going to be bigger than something that's divergent. So it's also divergent. Whereas if the integral converges, the series is going to be smaller than something that's convergent. So it's convergent. That's the whole kind of gist with the integral test. And then to be slightly more clear, we're kind of a little general here. We didn't say we had to start at 1. You can actually start kind of anywhere as long as both things are doing the same sort of thing. So we don't start when we say we can start at n, because it doesn't matter what the first n minus 1 terms of a series do, right? You can cut off the first billion terms. The end part is still going to do whatever the series is going to do. So if you cut off the first however many terms, the rest of it's either going to converge or diverge regardless of what the first however many terms did. because you're just cutting off a finite part of it. So if the whole thing's infinite, cut off a finite part, it's still infinite. If the whole thing's finite, cut off a finite part, it's still finite. All right, let's look at some examples. Like the sum from n equals 3 to infinity of the natural log of n over n. So this is where we're going to start to talk about developing kind of a flow chart for what you should try or what you should think about trying before you just jump to whatever the right thing is. So in the back of your mind, the nth term test should always be on deck. Nth term test should always be like, does that sequence converge to 0 or not? So what's the limit of our sequence? Well, limit as n goes to infinity of natural log of n over n, I'm going to have to use L'Hopital's rule. You get limit as n goes to infinity of 1 over n over 1, which is 0, which tells me nothing. It tells me that it doesn't automatically diverge. Right? We know we have to do more work to see if it's convergent or if it's divergent. Geometric series, definitely not an option here. Right? It's only ever going to be geometric if you have something raised to the nth power, and only that, right? You can't have anything else. So just as a kind of quick aside here, this series, n times 1/2 to the n, you can show it's convergent using other tricks, but it's definitely not geometric because each term isn't the previous term times the same thing. So it's not geometric. I don't think I can write it as like a telescoping sum. I have to use the new tool I have, which is the integral test. So I have to look at one, is my function, which is natural log of x over x, is f of x positive, continuous, and decreasing? Well, two of those I think are not hard to see. I think it's not hard to see that it is positive, at least starting at 3, it's positive, right? If x was between 0 and 1, it would be net natural log of those numbers is negative, but it's definitely positive for x bigger than or equal to 3. What about continuity? Where is this function definitely discontinuous? There's actually more than one right answer to that question, but it's definitely discontinuous at 0. And also it's not defined at any negative number, but certainly for x bigger than or equal to 3, this is continuous. Decreasing, on the other hand, is often something that's challenging to check. So to see whether or not a function is decreasing, we typically, if we can, rely on the derivative. It's not always an option though, because at some point you're going to have something that's going to have a factorial in it, and you're going to have to check it's decreasing by actually seeing, is the next term smaller than the previous term? But for us, we're just going to check and see, is the derivative negative? Okay, well, we can take the derivative of that. I'm always at the wrong part of the page, it feels like. Oh, well, we can still see the things. So our derivative here, quotient rule, let's see, bottom, derivative of the top, minus top, derivative of the bottom, all of the bottom squared. Simplifying that, that's 1 minus the natural log of x over x squared. When is this negative? Well, I'm going to make my sign chart like I usually would for a derivative. Now, I know that 0 is not in the domain, so really I should cut this off at 0. Like, none of that's any good. What's my critical value here? What makes this derivative equal to 0? Looks like it's going to be x equal to e. That's my critical value. Pick a number larger than e. What's a number larger than e that's easy to take the natural log of? It's not 4. It's not 5. It's e squared. If I plug in e squared to my derivative, I can see that f prime of e squared is 1 minus 2 over, I don't really care since it's positive. That's definitely negative overall. Okay, what's a number smaller than e I can plug in? It's easy to plug into the natural log. There's a more nice answer to this question. You can show me on your fingers. Yeah, exactly, right? Not e, right? You could like e and no. You can show me 1. So if you plug in 1, natural log of 1 is 0, 1 minus 0 is positive. So it's positive here. So that was really itches. Sorry. So this function's increasing and then decreasing, but specifically, f of x is decreasing if x is bigger than e, which is good because we needed it. We're starting at 3, so we're okay with that. Did you have a question? No, just okay. Sorry, I saw like a hand kind of go up. So checking that. Also good. Okay. So we're safe, right? This function, we can definitely see that f of x is decreasing if x is bigger than or equal to 3. So typically the decreasing one is kind of the one that's a pain to check. The other two things are usually not too bad. And in reality, a lot of teachers kind of like, yeah, let's just do the integral and not worry about the other pieces. Usually they're just fine. So some people might not mention this so much. But now let's check. So we're going to do the integral from 3 to infinity of natural log of x over x dx. All right, we need to determine, is this convergent or is this divergent? So that's going to be the limit as b goes to infinity of the integral from 3 to b of natural log of x over x dx. What's the integral of natural log of x? I mean, I said we could use the integral test here. Do we know how to integrate that? I mean, we do. We have to do a u sub. We're going to let u equal the natural log of x. Du is 1 over x dx. So the integral of natural log of x over x dx becomes the integral of u du, which is u squared over 2, which is the natural log of x squared over 2. So we're going to get the natural log of x squared over 2 from 3 to b and take the limit as b goes to infinity. And now I think we can see it's going to diverge because when we plug in b, we get the natural log of b squared over 3 minus the natural log of 3 squared over 3. And as b goes to infinity, the natural log of b also goes to infinity. So this is definitely going to go to infinity, which means it diverges. Kind of a lot, right? They're not short problems. Can you also just see that the bottom outpaces the top? No, because if I was thinking about the bottom outpacing the top, that would probably lead me to conclude that it was convergent. But we definitely are concluding that it's divergent. So I feel like that's not really what I'm going to, oh, or maybe you're asking, I'm not sure what your question is exactly, but I'm guessing maybe you're asking for when we did the limit right here to show that it was, I guess I'm not sure what, if you're asking about this limit or if you're asking about for if it's decreasing. Yeah. Unfortunately, no. It's because it's not always going to be the case, right? There are things where the bottom and the top are both increasing, and even if the bottom's outpacing it, it needs to be a little more specific, is what I'm trying to say. You're not wrong. That's a good idea, but we have to be a little more rigorous. Yeah. Because I made a mistake. Yeah, because I started writing. I think I saw the 3 here and just, yeah, it should definitely be a 2. Thank you. Now later on, maybe today, no, not today, we'll see an easier way to see whether or not this integral converges or diverges. There's actually a much more direct, pun intended, even though it's a pun, you might not know the punchline to yet, but there's a much more direct comparison for this. Or direct, you can use the direct comparison test. I'm trying to allude to in a not very suave way. So let's look at another example. Let's say we have the sum from n equals 1 to infinity of e to the n over 1 plus e to the 2n. You might like to see it. Okay, definitely not geometric. I should check the nth term test. So it's not geometric. Nth term, pretty sure if it diverged at the nth term test, I wouldn't be asking you it in this section, but it's good to check. Sometimes people like to throw weird curveballs in weird parts. So if I look at the the limit of e to the n over 1 plus e to the 2n, here we could argue that the bottom is outpacing the top, but we can also use L'Hopital's rule and say, oh, well, the derivative of e to the n is e to the n. The derivative of 1 plus e to the 2n is 0 plus e to the 2n times 2. And now we can simplify that. That's going to simplify to 1 over 2 e to the n, whose limit is 0. You also could have just divided everything by e to the n. That also would have worked just as well. And gotten the limit as n goes to infinity of 1 over e to the n plus e to the n. And then that goes to 0 and you get 0. That would have worked too. You don't always have to use L'Hopital's rule. It's just frequently that we do use it. Okay, so question.
What's the best way to determine if it's not geometric? Seems like I know that we spent like testing that.
So it is geometric if you can write it as, so a series is geometric if we can write it as the sum of some constant times some ratio to the nth power. But honestly, one way of seeing something's not geometric very quickly is write out the first 3 terms. So if I write out the first 3 terms here, my first term is going to be e over 1 plus e squared. My second term is going to be e squared over 1 plus e to the 4th. And my third term is going to be e cubed over 1 plus e to the 6th. And you could actually check, is the ratio from the third term to the second term the same as from the second term to the first term? It's not going to be, right? This divided by this is definitely not equal to that divided by that. So if you're pretty sure something's not geometric, but you're not 100% sure, write out the first 3 terms. And this divided by that has to equal that divided by that for it to be geometric. But really, if it's written in a way, right, this is written in such a way that it's definitely not geometric because we can't write it as just as one thing raised to the nth power. That's usually kind of what I'm looking for. So not geometric, nth term test is inconclusive, right? The limit being of the sequence being 0 means we don't know if it converges or diverges. And I guess we're going to go with the integral test because that's all we've got at this point. So we need to check our function. Our function is e to the x over 1 plus e to the 2x. It's certainly positive, right? No matter what x is, e to the something is positive. 1 plus e to something is positive. It's definitely continuous as long as it's defined, and it is defined everywhere. 1 plus e to the 2x is always bigger than or equal to 1, so we never have division by 0. And decreasing. I mean, it seems like it would be decreasing because, like someone was saying in the chat, the denominator is going to grow faster than the numerator. So you would think that would mean it was probably decreasing. But I want to be very, very clear. Just because a sequence is positive and its limit is 0 doesn't mean it's decreasing. It can do a thing where it like gets smaller and then jumps back up and gets smaller and then jumps back up and gets smaller. So it's not, so even though its limit is 0, it's not decreasing all the time. So we actually have to check. The derivative is bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. The nice thing about this is the denominator is never really in factor or in play because it's always just squared, so it's always positive. So we really just have to look at the numerator. That's going to be e to the x plus e to the 3x minus 2e to the 3x all over 1 plus e to the 2x squared. So that's looking like e to the x minus e to the 3x over 1 plus e to the 2x squared, or factoring out e to the x times 1 minus e to the 2x over 1 plus e to the 2x squared. And that's definitely going to be negative as long as e to the 2x is larger than 1. Or in other words, so it checks out. Most of the time, it's not super important to check this, but it is a condition that actually is supposed to be met to be able to use the integral test. All right, so then to the actually interesting part. What's the integral? So if I want to try and determine if this series is convergent, well, I'm going to look at the integral from 1 to infinity of e to the x over 1 plus e to the 2x. This might have been an integral you've seen before. It might not have been. There is a u sub we're going to do here. It might not be a super, I don't feel like it's an obvious choice. What is a plausible choice for you here? There's more than one answer. You could be, it's not, but you could be 1 plus e to the 2x. But it's not. And the reason that's not the choice I want is because my derivative isn't great. My du is 2e to the 2x dx. I don't have that. And I don't really want to make it so I do. I don't want to like multiply this by e to the x over e to the x. So there's a better choice. You either want to pick u that's stuck in something, or you want to pick u so that its derivative also shows up. Meaning, even though it might not be super duper obvious, e to the x is a great choice for you because the derivative of e to the x is e to the x. And I have an e to the x dx. So I'm going to rewrite the integral of e to the x over 1 plus e to the 2x as the integral of, well, there's my du. And then what do I have in the denominator? 1 plus u squared. And what's the antiderivative of 1 over 1 plus u squared?
Oh, no.
Oh, yes. Arctangent of u. Tricky. It's a little tricky. Do be careful if you're doing a u sub here and you're letting u equal e to the x. It could be really tempting to say this e to the x is equal to u, but you have to deal with the du part first. That's always the case when you're doing a u sub. You have to take care of this before you do anything else. So back to the actual integral. If we're doing the integral from 1 to infinity of e to the x over 1 plus e to the 2x, that's going to be the limit as b goes to infinity of the integral from 1 to b of e to the x over 1 plus e to the 2x. We know that the integral is the arctangent of e to the x. So it's going to be the limit as b goes to infinity of the arctangent, or inverse tangent if you prefer that notation. It doesn't matter. It's the same thing. And then we plug in our limits of integration. So we get the limit as b goes to infinity. This feels low. I feel like I'm hunching over here. Limit as b goes to infinity of the arctangent of e to the b minus the arc tangent of e to the 1. All right. As b goes to infinity, what does e to the b do? You've answered the next question, but you're right. So e to the b goes to infinity as well. And then the arc tangent goes to pi over 2 as the argument goes to infinity. So this is going to equal pi over 2 minus the arc tangent of e, which I don't care what that number is, but it is a real number. This is a real terrible number. But if it's a real number, that means the integral converges. So this integral from 1 to infinity of e to the x over 1 plus e to the 2x converges. I don't really care that it converges to pi over 2 minus the arctangent of e, because all I really care about is the fact that this means that my original series from n equals 1 to infinity of e to the n over 1 plus e to the 2n also converges. To what? We don't know, right? This test will not tell us what the series converges to. It'll just tell us that the series converges. And that's most of the time true. We're not going to know what a series converges to. We're just going to know that it converges. Okay, so the last thing I'll say, we're not going to do it right now, but I do want to tell you that you can also do the integral test for a very broad class of series called P series. So this series from n equals 1 to infinity of 1 over n to the p. You can show that this series converges by the integral test if p is strictly larger than 1. And this series diverges, again, by the integral test. I'm going to write if p is less than or equal to 1. Some people will say if p is between 0 and 1, because you don't need the integral test if p is negative, right? So just as a point here, if p is negative, for example, if I was looking at the sum from n equals 1 to infinity of 1 over n to the negative 2, there's no need to use the integral test to show this diverges. You could use the nth term test because this is really just which is clearly divergent. Since the limit as n goes to infinity of n squared is definitely not 0. But I still think it's worth saying this type of series, we can be very, very broad. We know that it always converges if that power is larger than 1, and it always diverges if that power is less than or equal to 1. So to keep in your minds, so someone just asked, what building is math dropping in? It's in the lower level of the library. And that's where I'm headed right after this. The two examples I would encourage you all to keep in your mind, because it comes up as something as a basis for comparison often, is this series diverges. It's called the harmonic series. And you should check that against this integral. Right? Integral test. You can definitely show that this integral diverges, and you should. That's good practice. In the same sort of way, this series converges because this integral converges. Yeah. That's it.